Let V be a vector space over field F and W be a subset of V. W is called a vector subspace, or simply subspace of V, if W is itself a vector space over F with the same addition and scalar multiplication as V. The following proposition gives us the criteria for a subset of a vector space to be a vector subspace. A subset W of a vector space V over field F is a subspace if it satisfies the following three conditions. Firstly, the zero vector is in W. Second, if W1 and W2 are in W, then W1 plus W2 is also in W. In other words, W is closed under addition. Third, for all lambda in F and W in W, lambda times W is also in W. In other words, W is closed under scalar multiplication. We label these three conditions as T1, T2, and T3, and we will refer to them from now on when necessary. To prove this proposition, we need to check that W satisfies all the vector space axioms. T2 and T3 ensure that addition and scalar multiplication are well defined in W respectively. As a result, A1, A4, S1 to S4 all hold in W because they hold in V. A2 is T1. A3 holds since if W is in W, then negative W, which is equal to negative 1 times W, is also in W. This completes the proof. Let's see some examples of vector subspaces. The first example, V and the set consisting of only the zero vector are always subspaces of V. They are called trivial subspaces. Second, the set of real polynomials R(x) is a subspace over the functions from the reals to the reals. Third, the set of polynomials of degree at most d is a subspace of R(x). 4. The set of real numbers contains trivial subspaces only. To see why, let W be a subspace of the real numbers, which is not just a zero vector. Then there exists a W in W such that W is not the zero vector. Then W contains all vectors of the form lambda times W, where lambda is a real number. Since this set is the whole set of the real numbers, which is contained in W, W must be the whole set of real numbers. 5. In R², take x to be the vector x1, x2, which is non-zero. Then S, which is the set of lambda times x, where lambda is a real number, is a subspace of R². Note that S is a line passing through 0. In other words, any line passing through 0 is a subspace of R². Let's also see some non-examples of subspaces. First, the upper half plane, which is the set of ordered pairs x1, x2, where x1 and x2 are real numbers, with x2 greater than 0, is not a subspace of R² because it is not closed under scalar multiplication. Indeed, if we multiply any vector by a negative number, then the resulting vector will have a negative x2 coordinate, which is not in the upper half plane. Secondly, the union of the x1 axis and the x2 axis is not a subspace of R² because it is not closed under addition. Indeed, if we add any two non-zero vectors in the x1 axis and the x2 axis, then the resulting vector will have no zero coordinates, which is outside the union. Let's see one more proposition. Let A be a m by n matrix with entries in F. Then the set S, which contains the vectors x in Fn, such that Ax equals 0, is a vector subspace of Fn. To prove this, it suffices to check that the subspace criteria T1, T2, and T3 hold. Since A times the zero vector is the zero vector is in S, so T1 holds. Suppose x and y are in S, then A times x equals 0 and A times y equals 0. So A times bracket x plus y equals A times x plus A times y, which equals 0 plus 0, which is 0. This means that x plus y is in S, so T2 holds. Finally, suppose x is in S and lambda is in F. then A times x equals 0. Also, A times bracket lambda times x equals lambda times bracket A times x equals lambda times 0, which is 0. This means that lambda times x is an S, so T3 holds.